Hello, welcome back to AmFed 2. Hope you are enjoying the series on electric vehicles. Today, battery management system BMS. Hope you are going to have a very wonderful session again.
On this episode, battery management system or BMS is our focal area. Let's refresh on the battery electric vehicles. Fundamentally, it uses chemical energy stored in rechargeable battery pack, and there is no secondary source of propulsion. So the conventional internal combustion engine, which we have seen the comparison in the previous episodes, there is no ICE or a fuel cell or a fuel tank in battery electric vehicles. We have battery electric vehicles in different segments, whether it's cars, four-wheeler, trucks, commercial vehicles, two-wheeler, motorcycles, forklift, and so on and so forth. Different types of batteries are used to power electric vehicles, and deciding which battery is best depends on its energy storage efficiency, the production cost, constructive characteristics, safety, and the lifespan, the longevity. Lithium-ion batteries are the most utilized technologies in EVs. EVs run on high voltage lithium-ion battery packs. Nowadays, there are so much advancement happening on materials. The batteries have higher efficiency, higher energy density, 100 to 265 watt hour per kg of the material. Compared to other battery chemistries, lithium ion has got 100 to 265 watt hour per kg. They pose a risk of fire under unusual circumstances. It is crucial to operate electric vehicles in predefined safety limits to ensure the safety of the user as well as the vehicle. What is a BMS, battery management system? It's an electronics management control or monitoring mechanism for a rechargeable battery, whether a cell or a pack or a module, and BMS becomes a crucial factor in ensuring electric vehicles safety. We used to see many accidents, fire hazards from EV due to the thermal runaway of the battery, the explosion, overheating, and similar incidents. The BMS safeguards both the user and the battery and thus the vehicle by ensuring that the cell operates within its safe operating parameters of temperature. The BMS monitors the SOH or state of health of the battery, collects data, controls environmental factors that affect the cell, and balances them to ensure the same voltage across cells. A battery pack with a battery management system connected to an external communication data transfer system or a data bus is referring to as a smart battery pack. It may include additional features and functions such as fuel gauge integration, smart bus communication protocols, general purpose input-output options, cell balancing, wireless charging, embedded battery chargers, and protection circuitry, all focused or aimed at providing information about the battery's power status. This information can help device conserve power intelligently. These are the different steps of battery production and usage. From a material processing, component production, from a raw material and different components are made. Then a cell production is done from the different components. The cell can be integrated to a module, battery module. Then the different battery modules can be put together to make a battery pack. So this can be integrated or assembled to the vehicle. After usage for certain life of kilometers or years of usage, the battery is deserving a recycling or a second life, a reconditioning. And the scrappage is also a major point in the battery usage or the battery product. A battery management system, a smart battery pack, can manage its own charging, generate error reports, detect and notify the device of any low charge condition, and predict how long the battery will last or its remaining runtime. It also provides information about the current, voltage, and temperature of the cell and continuously self-corrects any errors to maintain its prediction accuracy. Smart battery packs are usually designed for use in portable devices such as laptops and have embedded electronics that improve the battery's reliability, safety, lifespan, and functionality. These features enable the development of end products that are user-friendly and more reliable. For instance, with embedded chargers, batteries can have a longer life cycles, as the chargers charge the batteries to optimal ideal specifications within the temperature limits. Accurate fuel gauges allow users to confidently discharge batteries to their limits and not worry about the damaging the cell. GPIO, which stands for General Purpose Input Output, is an interface used to connect electronic devices and microcontrollers such as diodes, sensors, displays, and so on. Battery management system for electric vehicles. A battery pack from which the BMS takes the communication inputs regarding the current, voltage, temperature, and it gives out the state of charge, state of health, thermal management, power optimization, and it displays. Give a display. So it has a communication portal. So this is how, in a nutshell, we can illustrate how the battery management system operates. battery design, the electric car battery is talked about as a single thing. It usually consists of hundreds and if not thousands of battery cells that are connected in series or in parallel into battery modules. And these modules are then connected to a battery pack, or what everyone simply calls a battery. It is possible to achieve the required capacity and energy, and at the same time, every manufacturer makes a battery slightly different, uses different chemical compounds, or makes battery cells of different shapes. But it's always a type of lithium battery which is the most efficient technology that we have so far. These batteries are more or less sensitive to temperature changes, overcharging or discharging too much. And in order to prolong their life as much as possible, these quantities need to be carefully monitored and controlled. Lithium batteries are also prone to temperature leaks, which can occur due to several errors, such as charging too fast or discharging too quickly. The following graphs show the so-called safety operations area. The green box represents the conditions under which lithium batteries are safe and work the best. The temperature should be between -5 and 45 degrees Celsius. The voltage between 2 to 4 volts and the current from 0 to 1 ampere. It is paramount to carefully monitor and ensure that the battery is in the safety operations area. See, the assembly, the battery cell comprises put together to make a battery module, then that is integrated to make a battery pack. And the current versus temperature graph and the voltage versus temperature graph, we can see how it is varying in the operations and what could be defined as a safety operations area regarding the voltage and regarding the current against temperature. Two types of battery management systems are centralized one and a distributed one. A centralized BMS, as the name implies, has one control unit managing all the cells, which is very cost effective because we don't have to go for multiple units of controls. However, it exposes the entire system to a total failure. If single BMS fails, it affects the entire pack. And on the contrary, the multiple control units are commissioned to enhance system resilience in the distributed BMS. Now, this comes with increased complexities and cost. Automotive brands choose BMS system that based on their budget or the cost and the reliability factor. Obvious, the distributor one is reliable. If one fails also, it doesn't affect the complete operations, but it adds up to the complexity and also the cost against the centralized BMS. What are the functions of BMS in an electric vehicle? The first function is a cell monitoring. The BMS fetches real-time data on fundamental battery parameters like voltage, temperature, and current. With these matrices, BMS closely monitors important performance parameters like state of charge, denoting the amount of charge remaining out of EV battery's maximum capacity, and state of health, showing the overall status of battery pack health. SOC monitors helps EV customers assess their disposable driving range and plan their charging station stops without worrying much about the range anxiety. With SOC monitoring, EV manufacturers could practically assist their customers by providing heads up on preventive maintenance, retaining healthy battery conditions and prolonged performance. That is the function number 1, the cell monitoring. Second function is the thermal management. Electric vehicle batteries are sensitive to temperature variations, influencing their performance and lifespan. The BMS carefully regulates the thermal state of battery through constant monitoring and control of battery temperature values to maintain optimal operations. This can involve utilizing heating cooling mechanisms to keep the batteries within ideal temperatures or to maximize their performance and lifespan. Third is cell balancing. BMS includes a cell balancing process to make the energy cells perform uniformly. At a fully charged state, it equalizes the voltage and state of charge among the cells through two distinctive methods. One is an active balancing, which is transferring energy from overcharged to undercharged. Second is a passive balancing, where the excess energy is discharged through dissipative bypass mechanisms. Hence, no one cell gets overcharged or undercharged. Cell balancing increases the efficiency and longevity of the battery pack in an electric vehicle. Battery optimization. The BMS vigilantly monitors the multiple parameters of the battery packs. It has built-in protection for overvoltage, undervoltage, overcurrent, thermal management, and external overcharge or discharge incidents. In case of anomalies, the system will automatically regulate the predefined protection process, like optimized low voltage charging for damaged cells and balancing voltage variations due to oxidation to keep the battery performance optimal. This makes the BMS an essential component as it ensures the functioning, reliability, and safety of batteries used in electric vehicles, thereby enhancing the growth of eco-friendly transport for your potential consumers. Benefits of using a BMS in EV. The BMS has several significant advantages for EV. First one, the performance optimization. BMS helps derive the maximum performance of battery packs to extend the driving range and battery longevity through automated mechanisms to resolve anomalies and malfunctions pertaining to the battery. Second one, safety and reliability. BMS has complete monitoring and safety mechanisms for overcharging, draining, and temperature abnormalities. This ensures the safety and durability of a battery, thus minimizing accidents or failures for EV buyers. Third is real-time data and diagnostics. BMS observes batteries in real time, records data for logs on battery health, and identifies malfunctions. This helps OEMs schedule proactive maintenance to rectify issues and significantly enhance customer satisfaction. Current trends in BMS. Automotive OEMs consistently test new waters to evolve their BMS capabilities and strengthen their automotive offerings. And some notable developments in BMS space include intelligent BMS. By employing advanced algorithms and machine learning techniques, BMS can optimize battery performance according to patterns of batteries, utilization, environment conditions, and other dynamic scenarios. This advancement is valuable for automakers by reducing warranty claims and enhancing their reputation for reliability. External communication. Wireless communication protocols can be seen increasingly leveraged with BMS, enabling them to have system enhancement at speed through over-the-air updates. Meanwhile, with timely updates, automotive OEMs can ensure their BMS functionality and performance are intact. Advanced predictive algorithms. Battery management systems in electric vehicles are being integrated with advanced predictive maintenance systems. These algorithms rely on real-time data to anticipate when battery components may require repair or replacement, reducing customer maintenance cost, improving vehicle reliability, and enhancing brand reputation. As we can see, BMS capabilities are progressing by leaps and bounds with new technological innovations, and it is time for automotive OEMs to keep pace with this evolution.
An energy conversion megatrend is forming, and a high-growth, high-profile, mission-critical global battery industry is emerging with it. Stored energy has an accelerating and expanding role in tackling climate change and will become one of the most globally significant industries over the next 10 years. As governments worldwide get serious about decarbonizing their economies, demand for cheap, safe, high-performance, long-lasting, and low-carbon footprint batteries will soar, most notably from the automotive industry. The lack of low-cost, easy-to-purify raw materials to feed the world's existing and planned battery gigafactories is the biggest threat to supply security. The decline in investment in crucial mineral mines, coupled with the growing importance of environmental, social, and governance (ESG) factors, will restrict the development of new capacity. China's control of the entire global supply chain, from mines and refiners to component makers and cell producers, is a mounting geopolitical issue. Opposition to Chinese dominance is growing in Europe and North America, with both regions looking to reduce dependence on China within their supply chains. Battery recycling will grow significantly as these pressures mount, and Europe is in the vanguard. There will likely be a severe but temporary global battery shortage by 2025 due to a sharp increase in demand for electric vehicles, EVs, and a shortage of mined and refined battery metals. However, the industry is investing heavily to prevent this from becoming a sustained threat by reducing its use of scarce materials, developing new materials and battery technologies, and most importantly, developing a global battery recycling industry. Global data forecasts revenues in the lithium-ion battery industry of $408.3 billion by 2035, up from $88.6 billion in 2022 at a 12.5% compound annual growth rate (CAGR). Revenues from sales of lithium-ion batteries for mobility end users will drive much of the expansion, alongside considerable growth in consumer electronics and energy storage. Global data predicts that in every year of the 2020s, the automotive industry will add millions more units of EV capacity. This percentage will continue to grow into the 2030s, when EVs will ultimately account for most light vehicle production. Since EVs dominate demand in the battery industry, a trend set to increase in the future, how consumers use their cars is fundamental for automakers when deciding which battery chemistries to invest in. To help gain competitive advantages, auto majors and Tier 1 cell manufacturers are ramping up their use of simulation software and machine learning running on supercomputers to develop new materials and chemical combinations. Arguably, the single most important industry trend will be creating a massively scaled up battery and battery materials recycling industry, yielding a markedly circular battery industry by 2030. It will radically reduce the dependence on mined materials and the ecologically dirty mining industry.